Good morning, chemists. This is our first video in our series on solutions. So here's our title page. I've chosen a nice image there of a solution. It's something dissolving, and it's a compound called that we call rhodamine 6G, and it's a fluorescent compound, which means that it absorbs light and gives it out in a different wavelength. So this dye is commonly used as a tracer dye to measure the flow the flow rate and direction of water. So different engineers will use it and put a little bit in a water source, and they can measure the flow rate by how quickly it reaches somewhere, and the direction as well. And I've also seen it used in neodymium YAG lasers, a type of laser where you can tune the wavelength of it. So the wavelength that it pumps out of the laser, you can change that using these dyes. Okay. Our inquiry question is, how are chemicals in solutions measured? So how do we quantify the amount of stuff in a solution? And that's what this chapter is all about. So there's our syllabus dot points, only 3 this time. It's a shorter chapter. Okay, and a little bit of context that I've written. Let's see how well it goes. Excuse me. Homogeneous mixtures are common in nature and are manufactured. Okay, so you find what I'm trying to say is common in nature, and humans have manufactured these too. And on Earth, liquid water is commonly available, so it is a common solvent in solutions. So we're quite often talking about solutions where the solvent is water, so aqueous solutions. So many reactions occur faster in solution than other states because the molecules have easy access to each other. They're not locked up in a solid, they're free to move, they're free to hit each other from any angle. So reactions often happen in solution, and so therefore there's an importance to understand solution chemistry. That was a nice GIF, but that's not working, is it? Okay, a solution. A bit of revision here. So a solution is a homogeneous mixture. It's evenly distributed down to the molecular level. The solvent forms the majority of the mixture, and the solute is the minority. Okay. So something dissolves in something, but it's a little bit more complicated than that. The solvent is the majority, the most number of particles. The solute is the least number of particles. And these solutions can occur in all states, okay? Not just something dissolving in water, liquid water that we're used to. Solid solutions known as alloys, gaseous solutions like our air. And most of the solutions, as I just said, are liquid water with something dissolved in it. So I put together this animation. You can see it in the notes, where I've got this one here, which is going to dissolve in my solution. You can see it's all tightly packed together. The particles in here are all freely dispersed. It goes into the solution. It goes into the, well, it might not be a liquid. Let's just assume it's a liquid. It goes into there, and it freely disperses. So the orange is now completely dissolved in there. It's homogeneous down at that level. It's completely random, evenly distributed. Okay, also recall that substances dissolve into another because of the intermolecular attractions, and all intermolecular attractions have to be of a similar strength when you're dissolving something. If it doesn't dissolve. So the solute to solute attraction needs to be of similar strength to the solute to solvent attraction, and it needs to also be a similar strength to the solvent to solvent attraction. If one of these is stronger, say the solvent to solvent attraction is so much stronger, it won't form a solution at all. Okay, so here I've tried to show that graphically. It's not a graph, in an image anyway. So here I've got a solution, the one that we're talking about before, the pink and orange one. And here I've represented that the 3 interactions between the molecules are of similar strength because they've all got the same attraction arrows. And our examples are sodium chloride and water, oil and petrol will dissolve together, and oxygen and nitrogen will dissolve together too, because all three possible interactions are of equal strength in their intermolecular forces. Here I've got an example on the right where that's not true. Okay, here we can see that the pink is all up the top, and the blue particles, whatever they are stuck together down the bottom. That's not evenly distributed. It's not a solution, because if you look at the right here, look at how chunky this arrow is for the blue to blue. The blue to blue attraction is so much stronger that they just stick together, okay? The other two interactions are so much weaker, so you don't get a solution. Examples, water and oil, although if it was that, the oil will be floating on top. Barium sulfate and water. Barium sulfate's insoluble in water, and so is the next example, lead chloride, insoluble in water. So with those ones that are insoluble in water, these two here, the two salts, the attraction between the barium and the sulfate and the lead and the chloride, so much stronger than the attraction between the water of those and those. So they just stick together. Okay. Let's talk about dissolution a little bit more too. So you'll often hear chemists say ionization or dissociation interchangeably, but there is a particular difference between them. Okay, all three of these examples are dissolution, just different types. Okay, so let's start on the right hand side with molecular dissolution. Here we've got some covalent molecules, and they're going to go into solution into this water. And let's jump down here, and what ends up happening is they remain intact. Okay, they're surrounded by water molecules, but they remain intact, and that's called molecular dissolution. Okay, so they remain intact. Let's go up to the top here with ionic dissociation. We have an ionic compound here, positive, negative in a matrix, and we're going to put it in our solution of water. What ends up happening is it dissociates. Okay, so the positives go one way, the negatives go another. They're surrounded by waters. They're surrounded by water molecules in their particular way, so that the intermolecular forces are joined together. So your positives attract the delta negatives of the water. But the ions dissociate. They don't ionize because they were already ions in the first place, but they dissociate. Okay, so dissociation, ionic dissociation, just means that sometimes we use the term ionization when talking about an ionic compound going into water, but it's not true because it was ionized before it as a solid anyway. So if you want to be picky, you can pick up chemists on that, but we generally know what we're talking about. Ionization, if we're talking about ionization into dissolution, what we do have here is we have these covalent molecules. I'll get my pen going in a minute. We've got these covalent molecules here. They're not ions at all, and they go into solution. But what they do in the water is they form ions, they split apart, a bond breaks. And what we're left here, I'll zoom in a bit, we're left with this part and this part that are separate. So because we've broken a bond there, this half has got a positive charge and this half has got a negative charge. So we've formed two ions, a positive and negative ion there. Okay, so that's what happens to some covalent compounds. In water, they ionize, and you'll commonly know these as acids. So what we're representing there is acids, and we'll come back to that in a few more modules. Okay, we need to talk about concentration and how to express that quantitatively. Okay. Concentration is the expression of how much solute there is per unit volume of solution. How much of the stuff that's dissolved in a certain volume of the solvent. Okay, there's many ways to express that, and we'll talk about them soon. But as chemists, we like talking about moles, so we need a unit of moles. And we use the unit moles per litre to express concentration as a chemist. because that unit of moles allows us to equate molecule to molecule in a chemical reaction. Mass doesn't, okay? So, two ways to do this, okay? One, you can calculate the concentration using this formula, and this formula is on your data sheet and will be there in the HSC. Hopefully you do not need to consult it in the HSC. You should be using it so many times that you won't need it. But here's a formula for it anyway, okay? It's where big C equals concentration, little n on top equals the number of moles of solute, and V equals the volume of the solution in litres, okay? A nice little formula there, but you know me with formulas. You don't need this formula. All you need to remember is the concentration units is moles per litre. Moles over litres. It tells you take the number of moles of solute divided by the litres of solution. The formula is right there in the units, okay? So moles divided by litres, it's in the unit. There are other ways to express concentration, so not only chemists need to express concentration, but there are others. So up the top here, in my little table, I've given our one, molarity, moles per litre. So moles times litres to the -1, or sometimes, and usually in the HSC, they'll use the big M to mean moles per litre. So same unit, okay? I tend to use moles per litre all the time because it doesn't hide the units there, and we can use dimensional analysis to cross units out and multiply and divide and stuff. So I don't tend to use the big M, but we kind of have to get used to it because it's in our HSC. Another expression of concentration is parts per million. Parts of solute per million of solution, okay? So ppm is the unit, and a good common way to think of it, it's not the only way, but it's the most common way, is milligrams of solute per litre of solution. So it's measuring very, very tiny concentrations, okay? So parts per million, there's also a parts per trillion. You can kind of guess what that means, but that's talking about trace kind of contaminants in water and stuff like that. Very, very low concentrations. There's also percentage volume to volume, and that's the symbol there, percentage V/V, and that's equivalent to milliliters of the solute per 100 milliliters of solution. That is quite common, not with chemists, but I'll show you a few other ways in the next line. You've also got percentage mass to mass, so it's now changing the top of that to grams, and then the bottom per 100 grams of solution. And you've also got percentage mass to volume. Is grams of solute per 100 microliters of solution. I was just thinking that sometimes I've seen, I could be wrong, that these as percentage grams to grams and this as percentage grams to milliliters, but not often. Okay, and you've also got mass in a given volume, so someone might say there's 0.2 grams of lead per 100 milliliters, or you've got grams per litre as well. They're also quite common out there. Okay, let me talk about where we see these units. So some of these units are more suited to solids dissolved in liquids, like grams per litre and mass to volume. So it's talking about a certain amount of grams divided, a certain amount of grams in a volume, okay? Some are more suited to liquids, dissolved in liquids, so percentage volume to volume. And some concentrations are so small that parts per million is a handy expression to use. Okay. Environmental scientists often use grams per litre or milligrams per litre as they deal with small concentrations. So they're looking for trace elements, and usually toxic trace elements. So they tend to use milligrams per litre. Chemists, we work with moles, and there's a reason for that. But look on here, different things with different concentrations. Look at this label. 14% alcohol to volume. So we don't know what it's talking about, but I'd say it's percentage volume to volume. So it's saying that there's 14.0 milliliters of alcohol, or ethanol, 14 mil per 100 mil of solution. Okay, that's what it's talking about there. Should be a bit more specific. 14% what? It will be talking about volume to volume for those, because ethanol is a liquid at standard temperature and pressure, and so is water, so they'd be talking about percentage volume to volume. Here on the water, you'll notice they have an analysis of what's in there. Look at this. Fixed residue ammoniacal hydrogen. Oh, ammonium they're talking about. Nitrites. So they're measuring certain trace stuff. And look at what they're measuring it in the units. Milligrams per litre. Milligrams per litre. Okay, so small amounts. And another way that concentration is measured, so if you're looking at, if environmental scientists are looking at the amount of mercury in fish flesh, because that can be a danger, it can accumulate in there. Look at this, the amount of mercury milligrams per 1 kilogram of meat. So it's 2 masses there, talking about a concentration. 2 masses, milligrams of mercury in 1 kilogram of meat. Okay, as a chemist, we need to readily convert between all of them. Alright, I'm going to leave it there, and we'll do some examples in the next video.